Okay. Today we're going to have a sort of casual talk about DIY monitoring, and um, this is really sort of a brain dump of tools that I know of and I use to do job monitoring of the performance of jobs. This is not about some other things that we also do. So for instance, we do have profiling tools that will let you look at which parts of your code are consuming which fractions of time, execution time. They can profile the amount of MPI traffic and all sorts of great stuff. Those profiling tools are reasonably well documented. I think Sergey could actually give us a talk about map profiling. In fact, there probably is a recording. And we recently had a really great talk from Tyler about Python-specific profiling. This is also not about job profiles. Portals. We have job portals which are relatively new and not that well known among users, which give information about some metrics that we collect about your jobs. And these metrics are fairly highly aggregated and presented in sort of an operational format. So it's just a timeline with a graph. It doesn't, to me at least, it doesn't really invite an analytic approach to the data. It's more like detecting when something was really going wrong, or understanding that the reason your job was so slow is because you had prodigious amounts of I/O. There are also Slurm tools that give you some amount of feedback. In general, the feedback it gives you is so minimal that it's almost wrong. So really the only thing that you can trust in Slurm is the overall time usage once the job is complete. That's actually calculated per step, which is sort of useful, but it's aggregated across all the nodes, so you can't tell if some of your MPI ranks are imbalanced. It doesn't really give you any useful information about memory use. And again, that's aggregated in a way that prevents you from really analyzing it. And then there are classic tools like Top, Prof, and I guess it's now a classic tool, Perf, which I'll actually talk about. Perf is a Linux tool, which is much more flexible. It's actually sort of a kernel hacker's interface into the event counters that CPUs export. So I intend to talk about this information. I'm definitely open to questions if they arise, and I'll give a little demo. But what I'm really hoping to do is set up a situation in which we can figure out where we should go next for these tools. So it's fine to show you a Python script that gathers some information that answers some questions that come up. So for instance, we do get questions from users about CO2 footprint, and that's something that we can actually address to a certain extent. But the real question is how we should provide that to users, and whether users would take advantage of the data in a more open-ended analytic way, rather than a jobs portal that just gives you a time course for your job. I mean, for carbon footprint, it would actually be the entire job, but that's the idea. So I'm hoping that the very last thing, where do we go from here, is actually the main part of the talk. I actually have very few slides. I'm going to show you an example for a script I wrote. It was mainly to look at joule counters, which are exported by most modern processors now. Intel started it, and you'll see there's Intel mentioned on it, even though I'm going to be doing my demo on Narval. What the joule counters give you is a breakdown per socket, basically, of the joules, actually microjoules, used as a counter. So they just increase over time, presumably from reset. I didn't look up the details. It's probably a 64-bit count of microjoules or something like that. This is a narwhal node. It's the whole node. And as you can see, it's a AMD EPIC. I'm just going to run a script I wrote. Which prints out some information. I'm going to actually pause it here. So it prints out information about the counters available. And this is the full path. I mean, one of the themes here is that the information from these sources tends to be kind of hard to get to. It's not impossible for users to get to them, but they'd never know they were there unless they went looking. And there are probably things we can do to make it easier to access this. So in this case, for instance, these controls are exported under the PowerCap Intel RAPL kernel module, which is really weird because, of course, this isn't an Intel chip. And they're split into 4 pieces. So there are 2 sockets, and each socket is split into one main measure and one that they call core. So there are actually 4 bits of data that we're getting that are basically counters that are continuously updated. And the script I'm running is just showing you basically the watt usage of the job. Since I allocated the whole node, the fact that it's only showing me granularity of the 2 sockets is not bad. So on this node, you can see that it's claiming, I'm not sure how true that is, that the entire package is using 76 and 84 watts. So that's joules per second, basically. So each time I query the joule counters, I divide that by the time interval since I last queried the joule counters. And these numbers are quite low. I can actually show you the same thing on another node other than Narval, where I can also access power meters exported by the BMC, the management coprocessor, and they're very different. So the actual power per system here, oh, that's interesting. I hadn't seen that before. I guess that's a counter that wrapped and gave a negative number. Right, so I can also query on some systems, I can query the power known by the management processor, which tends to be more like 300, 400, or 500 watts for a dual socket CPU. This obviously only adds up to a few hundred watts. What do I want to say about this? In another window right now, I'm going to run I guess I should probably change the share so you can see what I'm doing. So I'm just running a script, a program I wrote called Thrash. It's actually a version of the stream memory benchmark, but it's kind of good because it generates a single stream workload of well-known properties. So this allocates 8 gigs of memory and then just keeps filling it with a constant character. And if we then go back to the original share here, we should have seen a burst of activity. Yeah, so here, when I ran that Thrash program for about 10 seconds, it showed a higher consumption. And I can't say that I really understand these numbers very well. They seem to behave roughly proportional to what I expect, what I what I get on machines where I can query IPMI. But I suppose it's something that we should probably investigate more thoroughly. If I run something more expensive, I'm just going to run a little GROMACS benchmark. Let me see. So I've got a little GROMACS benchmarks. It's currently set up. It's just GROMACS 2020.4. It's going to run 64 threads. It's the bench mem benchmark, which is sort of standard. It comes from the GROMACS website, I think. And I'm just going to run that. So GROMACS is doing its thing. And this is using all the cores, of course. And I'm going to switch back to the printout from Joules. So this shows a substantial difference. All the cores in use meant that we were seeing something like a total of 400 watts, which is pretty reasonable. Interestingly enough, the core, I don't understand why RAPL labels core as 4 watts and package as 200. Maybe my program screws up the labeling in some way, but I think the real take-home message is if you sum all these sum to about 410 watts, which is probably a pretty reasonable estimate for the power used as seen by the CPU. So that wouldn't be counting power used by RAM, it wouldn't be counting power used by the chipset or the efficiency of the power supply or anything like that. There's this other mechanism which isn't available to users where we query the management coprocessor, and that returns us, probably even on this node, it returns a substantially higher watts value. But you can see how if you can query these joule counters, then you could just print their sum before you run a program, print the sum after, subtract the difference, get the amount of joules you used, and multiply by 0.25 or 25 grams per kilowatt hour, which is, for instance, the current Ontario cost for these things. I guess I'll just go on with some other things. So I've only got, I think, one more slide that just lists these sorts of information. So I've talked about RAPL a little bit with joule counters. Perf is another tool which, unfortunately, we don't currently allow users to run, as far as I can tell, but we probably could, or we probably could extract information from perf and present that in some other way. Another source of information is C groups. The kernel maintains a lot of accounting on a per process, per C group basis. The C groups are basically, well, they're fundamentally the way containers work. And Slurm configures them primarily for resource accounting, but we can use them for those purposes as well. And then if I have time, I'll also mention just in passing that there are data collectors, which we usually call scrapers, on at least Cedar and Graham and Beluga, which provide information which might be more convenient to users. And I'll explain what I mean by that. But I'm just going to go back to a shell on Narval. So this is the same shell. I have a script called show my C group, just because the C groups, like the joule counters, are actually sort of hidden in confusing places on the system. So I guess the one I want to talk about mainly is the kernel C group set called CPU accounting. And in this case, this job, the information about this job and this step is found in this location, which is quite a mouthful. But if we go there, we see a number of controls exported by the kernel, which are potentially quite useful to us. So some of them are kind of obscure. Some of them have to do with the CPU scheduler. So for instance, CPU art, well, that's the real-time period. I think we're using CFS by default. So the CFS period in microseconds is 100,000 microseconds or 10 milliseconds. So, this is really obscure, but it means that the scheduler views time slicing and tells you that it views time slicing as chunks of 10 milliseconds, which is, I guess, potentially interesting to some people. The main thing I wanted to show is actually this CPU accounting -usage. And this is one of these counters that just increments. So if I do it again, it'll have incremented a little bit. Nothing very busy is happening in this, right? Nothing very busy is happening in this C group. So not much CPU usage is going on. I believe these are, I'm not sure what these units are, maybe hundredths of a second. No, it's incrementing much too fast for that. But these are actually the counters that Slurm uses to provide accounting information about where your job spent cycles. So Slurm actually gives you a breakdown of user versus system time, sort of like this. And you can get this information here as well. So if you just navigate to this terrible path, which, as you see, encodes both your user ID, the job ID, and the step, as well as task. I'm not sure why task is separate from step, but if you wanted to do this, you could actually gather this information incrementally in your own program and do some sort of analytics with it. So this is a 64 processor job. So I have 64 counters. I guess I could actually watch them change. Most of the CPUs are basically idle, as you would expect. I think there's a diff option. Yeah. This might make it easier to read. I'm just going to run the Gromax job again in the background. And yes, indeed, all the CPUs are busy and diffing. That's sort of reassuring. But there's actually more information available here too. So in general, this is the CPU accounting. It's broken down by CPU, but also overall. So this CPU usage all is, it's a good question. I'm not really sure what that means, but it's obviously indexed by core. I've been using CPU usage, which I think is just the sum across all cores. But there are also other C groups, and that's kind of interesting. So at any point, for instance, you might want to check, which CPUs you're actually allocated on. And if you go like this, this will list which CPUs, physical hardware CPUs, you have allocated on this node. You can do similar things with NUMA control. What is it, hardware? Yeah. So NUMA control is sort of the old-fashioned way of getting this information, but the C groups are really the truth of what the kernel is implementing. There are also other things like, for instance, you might well be interested in what your incremental memory use is. So there's no reason that you can't collect data from here. Again, this is a pretty awful path, but you can navigate to it. And if you do, you'll find that there's a lot of information about, for instance, here's your max memory use for this job. It's probably going to be quite low. So this is in bytes, which makes it a little bit harder to use. That's 8.6 gigabytes, which makes sense because one of the tests I did was a memory test of 8 gigabytes. I could do the memory test again on 16 gigabytes, and I hope it shows, yes, 16 gigabytes in use, or max. As an interesting thing, there are other options available. So memory is basically broken down into kernel memory, sort of normal memory, and then memory plus swap. But usually this is the one that you'd be interested in if you wanted to incrementally monitor your job. So it would look, so this C group is using roughly, what is that, 59 megabytes, which is about what you'd expect from a shell session. Not sure there's very much more to say about C groups, except that there's a huge amount of information available. So as you can see, if you want to find out where this information comes from, you can grep for C group proc mounts. These are all the types of C groups that the system has mounted. The kernel considers these to be virtual file systems, which is how it organizes the mounts. One interesting thing is that, so there's CPU information, which has primarily to do with, well, I'm not sure exactly, because there's CPU accounting and CPU set. I guess these actually might be a little bit redundant. It's not unheard of that the kernel would export similar information in multiple ways. But we've been talking about CPU accounting, and memory. There's also block I/O, which is a little bit less relevant for our systems that have a lot of Lustre activity, but it still exists. And if you're doing I/O to the local SSD on a node, for instance, it would definitely show up here. So you could look at throttling. I think we don't have configured, but we could. I think it's mainly just the block I/O service to bytes that would be interesting, which is 0. I guess I could probably demo that. This block I/O counter should have some different stats here now. To tell you the truth, I've never looked at the block I/O counting before. But that's the way I think of C group information. I guess I'm going to switch now to a little information about perf, which is a much different set. Well, for historic reasons, it's exported in a different manner. The perf counters are not shown in a virtual file system, unfortunately. So you have to use a tool called perf. Perf, it's pretty slow. Perf reads from registers exported by the CPU and interprets them. It's using a service in the kernel which treats these counters in a way that you can do sampling. So what I mean is that perf perf list tells you the sorts of information that perf can do. So for instance, you can do branch misses, you can do instructions, things like that. So if you do perf, I think it's stat, perf, oh. Right. So this command is using perf as a wrapper for the ls command. ls, I mean, looking in my home directory is not very interesting, but here are the sort of default set of performance counter outputs for ls. So it said that the program ran for 37 milliseconds, which is not useful to do anything with. But some of these sort of low-level details tell you a lot about how your program behaves. So for instance, 35 million cycles, 35 million instructions. It's potentially interesting that it's one instruction per cycle. You can easily imagine something that is more computational. So this is just that memory benchmark again. It's using a lot fewer instructions and it's executing a lot more cycles, which is what you would expect. Interestingly enough, there are quite a few branches, which is not too surprising because there's a loop in there that's just filling memory. I guess the most important thing about this is that if we go back to the perf list, you can get cache misses as a metric. So for instance, I can do the same thing here. And I'm running the same benchmark. And now it's going to tell me how many cache misses I had, which is potentially interesting. If I do this and say, I think this is the syntax. This tells me, cache misses per instruction if I divide those. I think if you use cycles, it's actually smarter and gives you a ratio. No, it doesn't. But that's 5 billion cycles and 5 million cache misses. So, you can say it's 1/1000th. That's actually really surprising. So that's 1,000 cycles per cache miss, which I guess is possible. This is a memory benchmark, so it's getting a cache miss basically on each cache line that it fills. Cache line is 64 bytes. So basically 64 bytes per, 1,000 cycles per 64 bytes is the way to interpret this. Anyway, perf is sort of a real rabbit hole if you want to follow all the detail that it provides, because some of these are generic and a lot of them are processor specific. So things like cache misses are meaningful across every processor. It breaks down a lot into things like LLC. And there you start to diverge between, say, Intel and AMD designs. But, branch misses, all sorts of interesting comparisons. I guess branch misses and cache misses and cache references might be interesting. don't know if it, yeah, right. So this is a memory benchmark on 4 gigs. If we ran the same thing on something much smaller, like, so there it's only 20 megs. I don't remember what the last level cache is on this processor, but a much lower fraction of cache references are cache misses in this case. So if we go up to 8 gigs, it'll have an even higher miss fraction. So here's something where, it's a very simple tool. It's just a wrapper for a single program. It's not aggregating across anything really. But it's providing us with something which is sort of intelligible on a microarchitectural level and tells us something about our program. And this isn't necessarily the best way to consume this data, but there's an abundance, a richness of data available with perf, which if people would like to use it routinely, we could certainly provide it in different ways. I have in mind a project to use a system called eBPF, which is sort of a way to extend the kernel in a safe and manageable way. eBPF would allow us to create a mechanism for users to query this sort of information on a routine basis. And it wouldn't have a high performance overhead. And yet, some of these metrics are pretty darn interesting. The cache misses, maybe you're interested in tuning your code based on cache misses, but there are all sorts of other things. This, interestingly enough, this does mention power, cores, package, and RAM. I haven't experimented enough to make sense of it, but well, just see what it does. Wow. Well, we'd have to check that out, but that's an interesting measure. So 49 joules for something that took 3.5 seconds. So that's sort of believable. Interesting. Anyway, I think it's a good example of things that might be interesting, and we can do a lot to make them easier to use. The same way we could do things to repackage information from C groups or the RAPL counters that would be more accessible, just because going through perf and going through RAPL and C group paths is kind of a pain. And users would almost certainly want to see it aggregated across, multiple nodes or things like that. One interesting thing about perf is that it is actually C group aware to some degree. So we might be able to collect this information. Well, I think it would only be worth doing if we could collect this information on a C group basis, which means that the kernel would do the heavy lifting in figuring out what's going on a node that has multiple users' jobs on it at once. This is an Intel-based node. If I switch back to an AMD node, it might be sort of interesting to look at the way its controls are different. It's got the basic things that you would expect, like CPU cycles, but now we're starting to get AMD specific things. Some of them are actually equated. So for instance, L1 caches, TLB information is something that we don't often talk about, but is pretty important, I think. So this is all IOMMU stuff, kind of in abundance. I haven't really looked at the AMD. Wow, so very detailed breakdown of floating point instructions. So you can have it, for instance, tell you, how many double packed divide flops well, you're doing, which is kind of astonishing if you think about it. How many multiply adds? That's pretty cool. It's even got x87 in here, which is ironic. I wonder if anyone ever executes x87 instructions these days. So it's got lots of memory stuff. All of the perf stuff is kind of rough around the edges. It's definitely not intended to be used, at least consumed without a lot of processing by end users, I think. But we could probably, at the very least, we could have a list of suggested perf queries that would tell people interesting things about their code. If we wanted to go big on this, I think we would probably treat it as a metric that we collect more like the portals and store for users. I guess I should, sorry, I did mention this scraping stuff, so I should probably show it. If I go back to this window, if you do curl localhost 9100 metrics, we use a system called Prometheus. Prometheus has an exporter on the node, and this is the syntax that it exports in. So there's infrastructure on Narval and Graham and soon Cedar that exports various metrics from the kernel using a fairly simple to parse syntax. Prometheus is the sort of monitoring infrastructure that we use that actually consumes this. But if you want, you could use it yourself. So this node buddy stuff is not necessarily that interesting, but there's a lot of other stuff available. So ZFS, packet information, right? So this is basically node level information exported by the kernel. There are other scrapers which we can also look at, and at some point, I don't know, maybe someone will get upset that these are exposed and they'll get hidden, but for now they're available and users could certainly scrape them. So this one, for instance, is more Slurm and C group aware. So it's exporting a bunch of metrics. You can see it knows which job it's executing within. It doesn't seem like it's all that interesting. I guess core usage is probably pretty interesting. So this core usage is basically a scraped version of those C group controls that we were looking at. But it's a different format and it might be more convenient to the user to get via this network interface. I think there's one more here. Right, so this is actually, right, so this is an exporter that's telling us about CVMFS, which is very unlikely to be of interest to users, but it's still there. I don't know whether these other ones are interesting. I chose a CPU node, so I'm not getting any NVIDIA information, but on Narval, for instance, there is an exporter that exports information scraped from the video card as well, the GPU card. And I think that's potentially interesting. Again, this is stepping on the toes of the portal. Simone's portal does an excellent job of using this information, presenting it to the user, but there are cases where the user might want the information in some other format. So maybe the user has, a job script that runs a whole bunch of different cases, and they want to collect the cache misses for each case. If we reported cache misses to the job portal, they could potentially extract that information and do the subtractions there. But, collecting it directly from the scraper might actually make more sense depending on what they're trying to do. And I don't think there's any real security implications of allowing users to do this any more than, we allow them to query the Slurm statistics from SACT or SQ. Mostly, I just wanted to talk about where we go from here, having seen some of these information sources. I guess I should apologize for not having presented a well-packaged program that makes all of these cleanly available in some generic way. But I think the real question is, which information will users and staff find most useful? And then we can consider what a good way to present that information is. In some cases, there would be additional infrastructure. For instance, perf is arguably not the right sort of interface for users to have access to. It's disabled on all of our systems by default, in part because you can cause real problems using it just by choosing the right settings. And there are lots of ways we have for users to shoot themselves in the foot, and maybe that should be turned off. Maybe they should be able to run perf, just the raw perf tool. But I think the bigger question is, should we consider it a project to extract that sort of information and present it in a cleaner way? More like a portal, or aggregating the information somewhat and storing it in a per job basis. I think those are really interesting questions. And I guess I'm done and would be very happy for some conversation.